Okay, so let's go ahead and get started. So what I'd like to do today is I'd like to begin by finishing our discussion of scattering amplitudes. And in particular, so far we've spent a lot of time in this course developing techniques and technology that allows us to calculate the amplitude that some incoming collection of particles will evolve to some outgoing collection of particles. And my goal today is just to delve into a little bit more detail of the procedure by which we take those scattering amplitudes and turn them into actual physical observables that we might see in some sort of particle physics experiment. So, for example, if you have some sort of beam of particles, then we would characterize that beam of particles by a flux. So you have some beam of particles here, and then you would have some flux, which is the number of particles in the beam per unit volume times the velocity of the beam, that is to say, the velocity of the particles in the beam. And then this flux basically characterizes, this flux basically characterizes the number of particles that are passing through some area per unit time. So for example, you can see this is proportional to the number of particles just by dimensional analysis divided by an area times the time. Okay. And what we want to do is imagine that we have some flux of incoming particles, and you want to count the number of particles that will scatter. Okay, so for example, you could imagine that you have particles that are scattering off of some hard source, a la Rutherford scattering, where you have some heavy gold atom here. You send in some particles to scatter off of that. Or you could imagine a more complicated scattering process where you have beams of particles that are colliding with one another. But in general, we characterize scattering in terms of what's known as the cross-section, which is the number of particles scattered divided by the flux of particles times time. Okay. And this, as you can see, because flux has dimensions of number of particles divided by area times time, this is an area, and it's known as the scattering cross-section. And in particular, if you have a beam of particles that's scattering off of some sphere of radius r, then if it's just sort of perfect hard scattering, then the total scattering cross-section sigma will just be pi r squared, which is the cross-sectional area of this hard sphere. More generally, what we want to do is consider this cross-section not the total cross-section, but you want to consider it as a function of the, say, momenta of the particles that you're scattering. Okay, so you imagine that you would have, say, some incident beam here, and you would have some sort of target that you are scattering off of, and then you would have some final scattering, and you want to calculate the number of particles that's scattering as a function, say, of the angle that this beam makes with vertical, or of the momentum of the particles, and so on and so forth. Okay. So what we're really interested in calculating is not sigma, but rather the differential cross-section. So let's say that we have a scattering into n final states, then the differential cross-section would be d sigma over d omega 1 up to d omega n, where these are all of the solid angles into which the nth particle scatters. So that, for example, the total cross-section, the total number of particles scattered, will be something like the integral d sigma over d omega 1 up to d omega n, integrated d omega 1 up to d omega n. Okay. I guess that's a sort of trivial formula. But the important point about these differential cross-sections is that whereas the total cross-section can tell you the cross-sectional area of the target, the differential cross-section will tell you something about the shape of the target. So, for example, if you have scattering off of a perfect hard sphere, then this leads to one characteristic formula for the differential cross-section as a function of this angle theta. This is known as the formula for Rutherford scattering, scattering from a hard sphere, and it's something that people sometimes compute in classes in quantum mechanics. So, for example, did you guys compute this in quantum mechanics? So this is a nice exercise if you haven't done this. The basic idea being that the dependence of d sigma on the scattering angle tells us about the shape, for example, of the target in the case of scattering from some sort of fixed target, or more generally, let's say if you have two particles that are scattering off of one another, that'll tell us some more complicated dynamics of the scattering process. Okay? And so the question is then, how do we compute this differential scattering cross-section from what we have computed so far in this class, which is the amplitude for some initial state to evolve into some final state. And so what I'd like to do is consider now what is probably going to be the most typical situation for the sorts of processes that we would study in this class, namely that of a scattering process where we have two incoming particles and n outgoing particles. So this would be in a typical sort of particle accelerator. You might have two incoming particles colliding in some beam and some number of outgoing particles. And what we would like to do then is calculate the scattering cross-section as a function of the initial momenta of the particles along with the final momenta. Okay. So what we would like to do is imagine holding the momenta of the initial particles fixed and calculating d sigma as a function of the momenta of the final particles. And then so schematically, the scattering probability is going to be proportional to the overlap between the initial and final states squared. That's just because a probability in quantum mechanics is the square of a transition amplitude, of a quantum mechanical amplitude. And all one has to do then is get all of the appropriate kinematic factors correctly. Okay. So already you would guess that d sigma should be proportional to the scattering amplitude squared. And now it's just a matter of going through the kinematics carefully to get the overall prefactor correct. Before I go through this, this is a computation that I started but didn't finish last class. Before I do this, let me just pause and see if there are any questions. Okay. So we've developed this Feynman diagram technology for computing these scattering amplitudes. Now we'd like to go ahead and compute this into something, turn this into something observable, a cross-section. Okay. Any questions before I continue? No questions? Okay. So, in particular, let's imagine, so just to begin, let's imagine that we fix the momenta of our two particles in the initial state, and we want to calculate the probability that you scatter into some particles with some final momenta. Okay. So the probability that you scatter into particles with some exact values of the final momenta is going to be infinitesimal. So what you really want to do is calculate the infinitesimal amount of probability, dp, that you're scattering into some final state where the particles have some momenta that are lying within some small range, say dp. So in particular, the infinitesimal probability, dp, that you'll have a scattering process where the initial and the final particles will scatter into a final state with some momenta, say dpi. So let's call these final state particles particles with momentum, say, p1 up to pn, then the differential probability is going to be proportional to the overlap between f and I, along with some normalization factor to keep track of the fact that these initial and final states are not necessarily unit normalized. Then we need some measure factor on the space of final momenta, okay? So which we'll call d pi. So d pi is the measure on the space of final momenta pi, where I runs from 1 up to n. And in particular, d pi is going to be the product, as I goes from 1 up to n, the total number of final particles, times the usual measure, d3p. Okay. So the measure on the space of final momenta. Yes, question. Squared. Sorry about that. Thank you. Good. Yes, that's why you were raising your hand. Thank you. Good. Now, the only thing that we need to keep track of is that this total probability should integrate to 1. And we've included these normalization factors here to make sure the norm of that, everything is normalized appropriately there. So we need to normalize this so that the integral over all possible, over the space of all possible final momenta of d pi should be equal to 1. Okay. So that means that there should be some normalization factor sitting right here in front of d pi. Okay. So in order to understand this normalization factor a little bit better, let's imagine the following. Okay. So let's imagine that instead of doing this experiment in infinite space, we were doing it in a space with a volume of size v. Okay. So imagine that we're doing this in a space of size v. And moreover, let's also imagine that we only want to do the experiment for some amount of time that I'll call capital T. So there are going to be various quantities that will arise when we take into account these kinematic factors that will appear naively divergent that I'm going to regulate just by imagining that we take the experiment to be done over some length of time t and in some large volume v. Now, at the end of the day, the answer that I'll get for the scattering cross-section will be independent of v and t, so I'll just be able to take them off to infinity. But just to make the intermediate stages sort of look reasonable, I'll imagine that I'm doing this computation in a space of finite volume. Okay. This is something that we may end up doing frequently in this course. Okay. So why do I want to do this? Well, the reason why I need to introduce this quantity v is that it's a dimensionful quantity. Okay. And it'll allow me to fix a normalization constant that's going to go right here such that the integral of d pi is equal to 1. So in particular, you see that if you stare at this equation here, okay, so d3p has units of energy cubed, okay, or length to the minus 3 power, because energy has units of 1 over length when c and h bar are set equals to 1, whereas 1 is dimensionless. Okay. So if you want the integral of d pi to be equal to 1, you need something here which has units of 1 over volume. So what that means is that d pi really has to be some dimensionless number times 1 over volume times d3pi, okay, with a product over all I of 1 over volume times d3pi. Okay. Now, actually getting the dimensionless constant out front correct is a little subtle. In fact, if you look in all of the textbooks where this computation is done, they just declare that this is true by dimensional analysis without discussing it any further. The reason why it's a little subtle is that if you imagine that you're in a space of if you imagine that you're in infinite space, then the momenta that you have are continuous variables, and you can integrate over them. However, if you imagine that you're in a finite space, momentum is discretized, and suddenly you shouldn't really talk about d3p, you should really talk about doing a sum over momenta. Okay. And d3p then is interpreted as the size of the little square in momentum space. So momentum is discretized, and you have one discrete momentum per little cube in momentum space. And the point is that the size of that cube is of order 1 over v. Okay, so that's where this volume factor comes from. And of course, the numerical factor will depend on things like what boundary conditions you put on the space of volume v. Okay, you could put reflecting boundary conditions, periodic boundary conditions for your modes, or something like that. But that's all going to disappear in the limit where you take v to be very large. So I'm just going to take d pi to be proportional to 1 over v times d3p for each factors of these external momenta. Is there a question in the back? Yes? Yeah. Yes, d pi should integrate to 1. Yes. So p is dimensionful. P has dimensions. Oh, I'm sorry. That's because, yeah, that's because there's a v here. Sorry about that. Yes. Right. I mean, yeah, sorry about that. Yeah. So p has dimensions of 1 over length. So p cubed has dimensions of 1 over volume. So you need a factor of v there, not 1 over v. Okay. Yeah, sorry about that. The point is that schematically, you should think of the integral d3p as going like 1 over volume. Okay. Good. Okay, sorry about that. Other questions? Okay, good. So now what we want to do is we want to compute this scattering cross-section d sigma. Okay. Now remember that the scattering cross-section is defined as the number of particles scattered per unit flux times time. So that's the d of the number of particles scattered per unit flux divided by time. And the total number of particles scattered is just going to be, well, the total number of particles scattered is going to be the total number of particles times the probability that some particle is going to scatter. So this will be equal to dp divided by the flux phi times the time for which you have this experiment running. And to compute the flux, well, let's just imagine that we have 2 to 2 scattering. Okay, so you have 2 incoming particles. And let's work in, say, the center of mass frame, where the 2 particles are both incident on some common target with some equal and opposite velocity. Then because you just have 1 particle, the flux is the velocity of the beam. So just remember, the flux is defined as the velocity of the beam times the number of particles per unit volume. Okay. The number of particles per unit volume is 1 over the volume of the space. So you have 1 over the volume of the space times the velocity of one of the particles that's in center of mass frame. Or in a general frame, V1 is not necessarily equal to V2. So this is V1 minus V2 over the volume in general, where the initial particles have velocities V1 and V2. Okay, so all we need to do to calculate this cross-section then is to take this formula for phi and for dp up here and plug that in to our expression for d sigma. So in doing so, all we need to do now is understand what these normalization factors are here, these initial and final state normalization factors. Okay. So what about, is there a question? Yes.
Should there be a factor of either 2 or 1 over 2 in this expression, in one of these expressions for the plot? Because if D1 is
Yeah,
equal
yes, I'm being a little sloppy about my factors of order 1 here. There are also some factors of 2 pi that I should have really put in here. Okay. So, I'll be completely honest, at the end of the day, if you need to calculate a scattering cross-section, what you're going to do is you're going to calculate a scattering amplitude using Feynman diagrams and then look up the formula, which will include all of the factors of order 1. So my goal here is to be very careful about keeping track of factors of order infinity, such as v and t and things like that, and keep track of any important kinematic factors, such as energy, momenta, velocity, things like that. But I'm not going to be very careful about factors of order 1. Okay, so yes, there is some factor of order 1. I'm not going to write it down. Okay, because once you start, because if you ask me to keep track of every factor of order 1, that way lies madness. Okay, good. Thank you for pointing that out, though. Yes, good. Okay, so what about the norms of the initial and the final states? Okay, so let's imagine that we have some initial state which has some momentum k. And we're interested in computing the norm of that state. Now, naively, you might say the following. Well, let's imagine we're computing the overlap between a state with momentum k1 and a state with momentum k2. Okay. This, as we learned, is proportional to k1 minus k2, and in particular should be a delta function. All of our states with momentum k should form some orthonormal basis that's delta function normalized. But the point is that, as you showed in one of your earlier problem sets, this delta function is not Lorentz invariant. And the norm of a state should be Lorentz invariant. It shouldn't depend on what sort of frame you're using to evaluate the norm of the state. So that tells you that you need a factor of 1 over omega k out front. Because this was the Lorentz invariant measure that was constructed from D3 of k. Explicitly, if you work everything out in terms of harmonic oscillators, the state k is 1 over the square root of 2 omega k times this raising operator acting on the vacuum state. And this raising operator obeyed the usual harmonic oscillator algebra, which you could then use to go ahead and compute the norm of this state, and you would get this expression right here. Okay. So what this means is that if you have a particle of momentum k, then the norm of that state is 1 over the energy of the particle with momentum k, the relativistic energy omega k, times a delta of 0. Okay. Now, of course, delta of 0 is infinity, but it's not really infinity because we're working in a space of finite volume. Okay. In fact, delta 3 of 0, well, it has units of, well, delta 3, let's put it this way. K has units of 1 over length. A delta function of x has units of 1 over x. So delta 3 of k has units of length cubed. So you would expect that this delta 3 of 0 in a space of finite volume is actually the volume of the space. And indeed, you can check this completely explicitly. So in particular, delta 3 of k is, we could use, for example, the definition of the delta function in terms of a Fourier transform. just set k equals to 0, and this is the integral d3x, otherwise known as the volume when k goes to 0. Okay. So if you have a single particle state where the particle has momentum k, then the norm of that state is the volume of space over the energy of that particle. Okay. Question? K1 and K2. Mm-hmm. Oh, I'm sorry. It's either K1 or K2. Yes. Thank you. K1 is equal to K2, so I just dropped the index there. Yes. Correct. Good. Okay. So what does that mean? That means that the norm of the initial state Oh, I'm sorry. I totally lied to you. There's no 1 over omega. There's an omega here. Right? That's what you showed on your problem set, right? Right. I'm sorry. I just wrote down the wrong formula. Good. Okay. So that means that the norm of an initial state of two particles with energy E1 and E2 is E1 times volume times E2 times volume. And likewise, the norm of a final state with n particles, each of which have energies E1 up to En, or each of which has energies EI, will be the product over all final particles of the volume times EI. And our final ingredient is we need to calculate the norm of this scattering amplitude. So up to some factors of 2 pi, the square of the scattering amplitude, remember, was some momentum-conserving delta function times this matrix element that we called M. M is the thing that we compute using our various Feynman rules in momentum space. And so we just need to square this. Okay. Now, you're not used to squaring delta functions, but, well, the delta function of x times the delta function of x could also be written as the delta function of x times the delta function of 0, right? Because the first argument sets the first delta function sets its argument to 0, so the second delta function is just infinity. Okay. But we've already learned how to deal with infinities so far today, because we're regulating the system by putting it at finite volume. So we're just left with a 4-dimensional delta function of 0. Okay. And what's the 4-dimensional delta function of 0? Well, the 3-dimensional delta function of 0 was volume, and so this is going to be volume times time. Okay, so let's put this all together. So we have the scattering cross-section is 1 over this flux times time times dp. So what were the various quantities that appeared here? So the flux, 1 over the flux was the difference in the volumes divided, the difference in the velocities divided by the volume. So that's 1 over the flux. Okay. Then we have a 1 over time. And then what was dp? dp was the overlap of f with I quantity squared, which is Vt times m squared times the momentum conserving delta function. And then we need to divide by the appropriate normalization factors. So we need to divide by the norm of the initial and final states so that everything is normalized appropriately. And so we get an E1 times V, an E2 times V, and then a product over all of the final states times VEI. And then we're finally left with this measure factor, d pi, which was the product over I of V times d3pi. Okay. So this is the final expression, or semi-final expression, for the scattering cross-section as a function of the various momenta in terms of this scattering amplitude that we compute using Feynman diagrams. Okay. And miraculously enough, this doesn't happen every time I do the calculation, but all of my V's and T's cancel. Okay. So you can take V and T off to infinity and get a scattering cross-section that remains finite. So you get the scattering amplitude squared divided by some kinematic factors, E1 and E2, and the difference in the velocities of the two initial particles, times some complicated measure factor that depends on the final states, which is a four-dimensional momentum-conserving delta function, and then a product over the momenta of the final states of our old friend, the Lorentz invariant measure factor, d3pi over ei. So this is some sort of Lorentz invariant measure on phase space, and in particular on the phase space, the momentum space of the outgoing particles. Okay, and there's some numerical factor of order 1 that I haven't been very careful of keeping track of. You can look it up in your book where everything is kept track of, including all the 2 pi's and stuff like that. It turns out to be a 4. Okay, sometimes constants of order 1 turn out to be 4. This is one of those times. Okay, you know, this is one of those calculations that is not particularly glamorous, but it's something that you need to do if you want to actually extract observable physics from all of these Feynman diagram calculations. In general, I think you're going to want to get familiar with working with relativistic kinematics. So a lot of the physics of scattering and quantum field theory can be understood only by thinking about some relatively simple kinematics, energy, momentum, conservation, and so forth. On the problem set that I'll hand out on Thursday, you'll get some problems where you'll get some practice for keeping track of this relativistic kinematics, working out the dynamics of 2-to-2 scattering and things like that in a little bit more detail. Okay. So I told you that most of the time in this class we would be interested in studying a scattering, say, of 2 initial states into some collection of final states. The other thing that you might be interested in doing, so the other sort of process which we commonly study, is not decay, is not scattering of 2 particles together to form n particles, but rather is the decay of 1 particle into n final particles. Okay. Yes, question? Sure, of course.
How does the sigma transform under Lorentz transformation?
Well, okay. So this measure factor is invariant. Okay. Yeah. So one actually has to be, so let's consider the case of scattering off of a sphere, say. Then you can see, so in that case, the answer for the total cross-section is the cross-sectional area. And you can see that that's something that's going to transform under when you do a Lorentz transformation. And in particular, so for example, if you have a sphere and you go to some frame which is moving with some relative velocity, then the sphere will appear squashed because of length contraction effects. And so you can see, indeed, that this cross-section should not be a Lorentz scalar, but should depend on what frame you're working in. And that's precisely what you see. Okay. You can see that this measure factor here is Lorentz invariant, but I've done things like write down the energy and velocity in some particular frame. So if you did some Lorentz transformation, E and V would transform into one another in some complicated way. But the one thing I know about this quantity here is that it's not a Lorentz scalar. It's not E squared minus V squared, okay, which would be the only Lorentz scalar. So that's telling you that d sigma really is not a Lorentz scalar, but depends on what frame you're working in.
It's neither a vector.
It's not a vector either. I think the example of scattering off of a sphere is a good one to think about. Good. Excellent question. Yeah. Good. Other questions? Yes.
The integral of dp over the measure should be what?
The integral of d pi, yeah.
So the probability.
Yeah. The total integral of d pi, dp should be 1, right? If one also sums over all possible final states, right? The one thing you know is that probabilities are conserved. That's the unitarity of quantum mechanics. So if one summed over all possible final states, not just their momenta, but all possible final constituent particles, 2 particles, 3 particles, and so forth, you should get 1. Okay? But of course, for any given fixed number of final particles, you're not going to get 1. Yeah, that's a good question. Yes. But we did normalize we included a normalization factor in d pi so that it integrated to 1, but dp will not integrate to 1. But we just pulled out that normalization factor so that all of the non-trivial stuff in dp would come from, would come from this guy here, not from this guy. Okay. Good questions. Excellent. Okay. So if one's interested in studying a decay process rather than a scattering process, then you don't want to compute a scattering cross-section. Instead, what you compute is a decay rate. Okay? And the decay rate is typically denoted gamma, which is the total probability that some particle will decay per unit time. So that would be, say, the number of decays. So the number of particles that decay per unit time times the total number of particles. So one has to divide by time, of course, because if you have some sort of unstable particle and you wait long enough, then the probability that it will decay is 1. Okay? So instead we calculate the probability of decay per unit time. And again, one can also consider gamma not just the total number of decays, but the probability that a decay process will happen with particles heading out with a particular combination of final momenta. Okay? So similarly, one can consider d gamma, which will be 1 over t times some differential probability, to be the probability per unit time of a decay into a state with n particles with some particular final momentum or that is momenta, labeled by pi. Okay. And then a very similar computation to the one I gave above gives you this d gamma. So the answer is almost exactly the same as what we wrote up here, except it's even simpler. So this Lorentz invariant measure factor will be precisely the same. Okay, so let's give that a name just so I don't have to write it down again. I'll call it d pi lips. Lips stands for Lorentz invariant phase space. Then d gamma will just be a very similar looking kinetic factor. So we only have one particle, initial particle, which I'll take it to be in center of mass frame so that it's not moving. So this will be the energy of the particle. So that's the only piece of kinematic data about the original particle. And then we'll have this Lorentz invariant phase space measure. Okay. And that'll be in center of mass frame. And of course, one could work in some other frame, and then the decay rate would be different. Okay. So for example, if you have some decay rate in a rest frame, then in some other frame where the particle is moving, the decay rate would be much less. Okay, that's because of time dilation. So for example, a famous example that you guys may have encountered before is that the muon has a very short lifetime, but a muon can also travel. A muon can also travel a very long distance before it decays, because it's traveling very quickly. And so the proper time that some muon that's moving very close to the speed of light will experience can be very, very short. So there's a very small probability that it will decay. So I don't remember the exact numbers, but muons that we observe here on Earth are typically created by the collision of cosmic rays with particles in our atmosphere. If you just use the naive decay rate of a muon at rest, you would think that those particles would only get a few feet in the atmosphere before decaying. But because they're traveling at relativistic speeds, very close to the speed of light, they actually will arrive here on Earth. Okay. One of the classic experiments that people are usually tortured with in undergraduate or graduate labs is actually measuring these muon, these cosmic muons from cosmic rays. Okay, good. Okay, so you now have all of the ingredients that you need, at least in principle, to go ahead and compute scattering and decay processes. Okay. So, for example, we could imagine that you have a theory with two species of particles, say, let's call them chi's and phi's, which are coupled via some coupling chi phi squared with some coupling constant. Then you could go ahead and compute the decay rate, and it would be equal to some kinematic factors times g squared. Okay. Coming from the Feynman diagram, where one chi splits into two phi's. Okay. And it will be proportional to and it will be proportional to these various kinematic factors as well. Or similarly, one could calculate the scattering cross-section for two phi's to scatter into two other phi's via the interchange of a chi particle, and that would be proportional to g to the fourth, because it's the square of this amplitude. And then it's just a matter of doing the calculation in order to calculate the dependence on energy, on the various scattering angles, and so forth. And that's something that you have the tools, at least in principle, to do now. Okay. So later on in this course, we'll get to quantum electrodynamics. That's going to be the sort of end goal of the first semester of this course. And we'll end up doing some very explicit calculations of scattering processes and that sort of thing in quantum electrodynamics. So at this point, what I'd like to do is maybe step back a little bit, talk a little bit about the big picture of what we've done in this course and where we're going, before diving into the next major topic in this course, which is going to be quantum electrodynamics. So far what we've done in this course is we've seen that the combination of quantum mechanics and relativity necessarily leads you to a field theory. We've considered a very simple field theory, namely the theory of scalar fields. And we've understood the computational process that you would use in order to calculate scattering processes, decay processes, and in general all the various observables of a scalar field theory. And we've developed techniques that work in some sort of perturbative expansion where you have a small coupling constant, so that the theory is nearly free and that interactions in the theory are very weak. So what I'd like to do now, and what we're really going to do for the next couple of weeks, is develop a slightly more complicated set of field theories. That is to say, not scalar field theories, but theories of particles with spin. And the reason that we're going to do this is that, of course, all of the particles that we see in nature, except one, are particles with spin. Okay. So what we really need to, so the next, say, few weeks in this course are going to be devoted to understanding how we generalize these various techniques that we've developed for particles without spin to particles with spin. Okay. So all of the particles that we see have spin. Okay. So for example, all of the various matter particles, quarks, gluons, protons, neutrons, electrons, positrons, and so forth, all have spin 1/2. And all of the various force-carrying particles, photons, gluons, W's and Z's, the carriers of the strong and weak nuclear forces, as well as gravity, well, actually, not as well as gravity. All of the photons, gluons, W's, and Z's all have spin 1. And the other sort of particle that we see is the graviton, which is a particle with spin 2. Okay. The only particle that we have observed that has spin 0 is the Higgs. Okay. If I taught this class 2 years ago, then I wouldn't be able to say that. Okay. But we do actually now have evidence for a particle, a fundamental particle, or apparently fundamental particle of spin 0. But all of the processes that dominate at low energy, that is to say, the processes that we can observe in anything except very, very expensive particle accelerators, all involve particles with spin. Okay. So we're going to need to spend some amount of time over the next few weeks developing the machinery to study particles with spin. Okay. Now, there's really nothing particularly more complicated about studying particles with spin than there is of studying scalar particles, particles without spin. But the formulas can get significantly more complicated. So we'll still be using Feynman diagrams. We'll still be using the same set of diagrammatic techniques. We'll still be using the same set of, basic processes to calculate quantities when we study particles with spin. But unfortunately, the algebra is going to get significantly more complicated. So that's why typically when people study quantum field theory, you spend some amount of time getting used to studying things in scalar field theory before moving on to particles with spin. Okay. So what I could do now is give you a very general kind of systematic development of how it is we think about spin and quantum field theory, and how it is we study in general field theories of particles with spin. But instead of doing that, what I'd like to do is at least spend the next 1 or 2 classes talking to you in some amount of detail about the particle with spin that you already know very, very well, and the field theory that you already know very, very well. Namely, that's the theory of electromagnetism. Okay. So the simplest field with spin, and in particular it's a field with spin 1, is one that you already know. Okay. In particular, it's the photon, and the field theory of the photon is electromagnetism. So in particular, at the level of classical field theory, you've already, spent a lot of your life studying the equations of motion of the field theory of a particle with spin. In particular, you've studied Maxwell equations. Okay. Sometimes in quantum field theory, we give a very fancy name to electromagnetism. We call it a U1 gauge theory. The reason being that, in fact, the other force carriers in the standard model of particle physics are generalizations of the electromagnetic field that have more degrees of freedom and have some slightly more complicated structure. For those cases, those fields are different sorts of gauge theories where U1 is replaced by a different group, SU2 in the case of the weak nuclear force, or SU3 in the case of the strong nuclear force. But for the time being and for the rest of the semester, we'll just be focused on the simplest gauge theory, that is to say electromagnetism. Okay. And my goal for the next week or so is to develop the theory of electromagnetism as a field theory. We'll quantize it just as we quantize the scalar field theory. There's a sense in which electromagnetism was the very first system that was ever quantized because Planck's derivation, Planck's resolution of the ultraviolet catastrophe for black body radiation involved the quantization of the electromagnetic field. Okay. He didn't know that's what he was doing, but now, after years of taking quantum mechanics and now taking quantum field theory, you can return to your roots and understand Planck's resolution of this ultraviolet catastrophe as we quantize the electromagnetic field. And then what we'll do is we'll study quantum electrodynamics. Okay. In order to do that, one needs to also understand spin 1/2 particles because the electron has spin 1/2. And before diving into that, the sort of mathematics of particles with spin and quantum field theory can get a little complicated. So before we do that, we'll just study a sort of toy model of quantum electrodynamics where you forget about the fact that electrons have spin and you just think of them as scalars rather than particles with spin. So that's so-called scalar quantum electrodynamics. I think by the end of this week, we'll probably have most of what we need to study quantum scalar QED. And this is a theory where you can start calculating things, the sorts of things that you would actually observe, in sort of realistic quantum electrodynamics processes. And many of the answers that you get will be very close to the answers that you would get in actual QED. Okay, just some factors of order 1 that are different because you're not taking into account the spin. Okay, and so really I think the goal of our course this semester is to give you a complete and systematic picture for quantum electrodynamics and to start computing things like the anomalous magnetic moment of the electron, Bremsstrahlung, scattering processes, and so forth. And then what we're going to do next semester is we're going to kind of understand a little bit more deeply the structure of the theory. We'll talk about renormalization. We'll talk about the various infinities that have already popped up so far. When we talked about tadpole diagrams, we encountered infinities. On your problem set, when we talked about the energy of the vacuum state, you encountered infinities. So what we're going to do starting next semester is delve a little bit more deeply into the theory of how it is we deal with those infinities. This is a theory of renormalization. It's probably the deepest and most important subject in quantum field theory. It has importance in particle physics, condensed matter physics, statistical physics, all over the place. And then after understanding renormalization in a bit more detail, we'll move on to studying the full glory of the standard model of particle physics. Okay. So that's kind of our grand plan. Sort of having now spent the first 6 or 7 weeks of this course developing kind of the nuts and bolts of the most simple field theory, we're now going to start developing some of the more complicated aspects of the field theories that we use to describe nature. Okay. So I just wanted to give you a little diatribe so that you would have a little context of where we've been and where we're going. And what I'd like to do now is just spend a couple lectures talking about the quantization of electromagnetism. Okay. Before I go on, are there any questions? This is a good chance for big picture questions. Okay. A door is closing, a new door is opening, so on and so forth. Something like that. Yes. Good. Okay. Okay, so when we study electromagnetism, we're studying a field theory where the basic field, that is to say the dynamical variable that we use to describe electromagnetism, is not a scalar, which is one function of a point in space-time, but a set of four functions, a mu, which is a Lorentz four-vector, whose first component is the electrostatic potential, or the electric potential, and whose other three components are the vector potential A. And this describes a particle with spin 1. By the way, people are sometimes a little bit confused by the statement that a photon has spin 1. It can sound a little bit mysterious. When we say that the gauge field, the electromagnetic field A mu, has spin 1, what do we mean? We mean that it has one index here. Okay. Spin 1 equals one index. A scalar field is called a spin 0 particle because the field phi has no indices. A graviton is called spin 2 because g mu nu, the metric, has two indices. And an electron is called spin 1/2 because an electron has half an index. Okay. That was a joke. It's sort of true though. Okay, it's sort of true. That's one of the reasons why spinors are a little complicated, but it is sort of true to some extent that an electron is described by a field with half an index. To say that a little bit more, less glibly, our vector A mu is described by an index mu that takes four values, 0 up to 3 or 1 up to 4. And an electron is described by an index that takes two values, okay, 1 or 2. And 2 is half of 4. Okay, so what are the equations of motion of electromagnetism? Well, they're Maxwell's equations. And in, yes?
Can I just ask a question about that statement?
Sure.
You also said that the graviton should have spin 2, but there are
Yes.
10 degrees of freedom in the metric
Yes.
tensor, which is not 2×4.
That's an excellent question. That's because when we characterize particles, you need to talk about more than just their spin. You need to talk about what representation of the Lorentz group they transform under. A graviton is not just any two-index object. It's a two-index object that's symmetric in its two indices. And so a 4×4 matrix, which is symmetric, has 10 degrees of freedom. So in fact, there are two different kinds of spin 2 field that you could write down. There's the graviton, which is the symmetric spin 2 particle, and there's an anti-symmetric spin 2 particle. Nobody's observed such a thing. We don't know if such a thing would exist in nature. But there are many cases where if you study the, what's called the low energy effective dynamics of some system, you can describe it dynamically in terms of some spin 2 field. Okay. So there are cases where you might want to use spin 2 excitations, anti-symmetric spin 2 excitations like this, okay, rather than symmetric ones. For example, all the various, there are all sorts of various unstable particles with very high spin that are made up of bound states of constituent objects. And some of these have spin 1, spin 2, spin 3, and higher. And the spin 2 ones, they're both symmetric and anti-symmetric ones. Okay. Now, they're quite different from the graviton. So the graviton is special because not only is it a spin 2 particle, but it's massless, which means that it's a long-range force. Its excitations, travels at the speed of light. As you saw when you computed 2-point functions. The 2-point function of a massive particle falls off exponentially in the mass, whereas a massless one only falls off quadratically. Okay? That's why massless particles mediate long-range forces. That's why when we do astronomy, we do it with electromagnetism rather than with rather than with the weak or strong nuclear force, okay? Because the force carriers, the particles of the strong and weak nuclear force, have mass, and that means that the length scale on which these forces propagate is very, very small. Okay? Or that is to say that a little bit more differently, the nuclear forces are very, very strong at short distances, but very, very weak at long distances. Okay. Yes, that was a kind of long answer to your question, but hopefully that was clear.
What would be the spin 3/2 particles in order to
Good. Yeah. So there, spin 3/2 particles are postulated. People look for them. They're typically called gravitinos. There's a sort of one of the typical naming conventions is that often, yeah, okay. Often theories with half-integer spin have an eno at the end, but let's not yet go into that. So yes, people do look for spin 3/2 particles. Nothing's ever been seen. People do look for signatures in the cosmic microwave background, actually. I should mention, if you don't know already, that one of the important applications of quantum field theory is to the early universe. In the early universe, our universe is expanding. In the early universe, the universe was very, very small and very, very hot. That means it had a lot of energy, far more energy than in the during collisions of the LHC, which means that in principle the dynamics of the early universe was governed by a very different state of matter than is present now. Okay? So people imagine that there might, for example, be a spin 3/2 particle that is very massive, so that we can't see it now. Okay, but its mass scale was very, very small compared to the energy scale in the very early universe, so that we could see the effects of the spin 3/2 particle in the early universe. Okay. You've probably you've probably heard a lot about BICEP, or maybe you haven't. I don't know what sort of where you get your news, but people look at the cosmic microwave background and then they see the polarization structure of the cosmic microwave background, and this is literally seeing the quantum excitations of a spin 2 field in the early universe. Okay. So one of the things that people made a very big fuss about last spring was the claim that observation of polarized light in the cosmic microwave background. This was literally, the claim is that this is literally the quantum excitations of the graviton, a spin 2 particle, during the very early universe. Okay. Turns out that claim was sort of overblown. They didn't quite understand the data, the foregrounds, blah, blah, blah. But okay, that's the sort of thing that we're talking about. So when we talk about the quantization of fields with spin, that's something that's interesting. Okay, yes. What was the question again? I don't remember.
Just the case of spin 3/2.
Yeah, nobody's seen one. That was I could have answered that question much more easily. Yeah.
So you mentioned the gravitino specifically.
Yeah.
Supersymmetric partners,
Yeah.
particles in general.
Yeah. There's no evidence for supersymmetry in nature.
Yeah.
Yes.
And more about what spin the particles have.
Okay, so, okay. Sure, okay, yeah, let's just, okay. So, yeah, supersymmetry is pretty interesting. So in the way that we saw this up here, we saw that all of the matter particles have half-integer spin, and all of the force particles have integer spin. Okay. And so there appears to be not much of a relationship between them, but people have postulated that there's actually a symmetry that relates all of the force-carrying particles to all of the matter particles. This is known as supersymmetry because it's super. It relates particles with, say, spin 1/2 to particles with spin 1. And if this symmetry is true, if nature has this symmetry, then there should be a particle of spin 3/2, which is the partner of the graviton known as the gravitino. Okay. And so people look for gravitinos. People look for them at the LHC. People look for them in inflation. They haven't seen them. Okay. People also look for other sorts of supersymmetric partners of different particles. Okay. So for example, supersymmetry postulates that for every force-carrying particle of, say, spin 1, there's another particle of spin 1/2, which is the partner of it. Okay, so for the W particle, yeah, okay. I told you people like putting eno at the end of particles. So for the W particle, they called the wino, W-I-N-O. The BNO is the particle of B, stuff like that. For every matter particle of spin 1/2, you expect a spin 0 or a spin 1 force-carrying particle. And people usually put an S in front of that. So you're looking for the selectron, which is the partner of the electron, or, I don't know, the squark, or the stop, which is the partner of a top, a quark or a top. So, there are all sorts of, we haven't gotten to the standard model yet, so we're getting a little bit ahead of ourselves. But yes, we don't know what the correct theory of nature is. Okay? All we know is what the correct theory is that describes nature at very low energies. We understand it pretty well. Okay? But we don't know, we certainly don't know what's out there. Okay? Good. Yes?
You were implying that GU or the tensor has to be other symmetric.
No, so the metric tensor is a symmetric two-index object. Okay. So, yes. So there are other spin 2 excitations which are antisymmetric. I guess your question is, does it have to be either antisymmetric or not antisymmetric? That's a very good question. So this gets to something that we'll talk about a little later. It gets back to what we mean by a particle. Okay. What we mean by a particle is something that transforms under the symmetries of space-time, okay, under the Poincare symmetries. In the mathematical language, we call something that transforms under symmetries a representation. And but what you want is a set of states that transform into one another under these symmetries. But you don't want to be able, you want it to be what's known as an irreducible representation. And what that means is that you don't want some set of states to transform only among themselves and some other set of states to transform only among themselves. That you would call two particles. Okay. So for example, it turns out that if you had a general symmetric two-index particle, a general spin 2 particle, G mu nu, where G mu nu was not symmetric or antisymmetric, then you could separate it out into two things that wouldn't transform into one another, that wouldn't mix. So if you had something that was neither symmetric nor antisymmetric, I would say actually you have two particles, an antisymmetric one and a symmetric one. Okay. And in fact, I would also say you have three particles. You also have a scalar one because you could take the trace of the metric. Okay. So a general spin 2. So we haven't gotten into group representation theory. We will, don't worry. But a general, say, spin 2, two-index object would be could have three possible structures. There could be the scalar mode, the antisymmetric mode, and the symmetric mode. Okay. Good. Okay. Any other questions? Okay. Good. Okay. Now, you all had a problem set at the beginning of the course where you worked out a few of the details of the description of Maxwell's equations and electrodynamics, electromagnetism, in the language of quantum field theory, in a Lorentz invariant language. So let me just remind you of a few of the things that you derived on that problem set. So in particular, we're used to dealing with an electromagnetic field in terms of an electric field E and a magnetic field B. But when we're talking about special relativity, it's very convenient to combine these into one single object, which in fact is an antisymmetric two-index object, known as the electromagnetic field strength tensor F, which is defined so that its 0I components are the electric fields, and its ij components are the magnetic fields. So this would be epsilon ijk, bk. These combine to form an antisymmetric two-index object, which is a 2 tensor known as the electromagnetic field strength. Okay. You can see an antisymmetric 4x4 matrix has 6 degrees of freedom, and those are the 3 degrees of freedom of the electric field and 3 of the magnetic field. And this is useful, of course, because F mu nu transforms as a tensor under Lorentz transformations, and this tensor transformation law encapsulates the rather complicated transformations of the electric and magnetic field into one another under a Lorentz transformation. Okay. For example, how E transforms into B under a Lorentz boost. Okay. Now, the electric and magnetic fields are given by the derivatives of the electromagnetic potential phi and the vector potential A. And so, correspondingly, one can write down an equation for the electromagnetic field strength as the first derivative of the electrostatic potential A mu. And because it's F mu nu is antisymmetric in its indices, the only thing that you could possibly write down is this particular antisymmetric combination of derivatives that I've written here. Okay. You guys did this on your problem set, is that correct? Okay, so this should all be reasonably familiar. One nice thing about this formulation of electrodynamics is that Maxwell's equations are rather simple to write down. They take the form, so one of Maxwell's equations says that the gradient, the divergence of F mu nu is equal to the current. So this is the current for vector. And the other of Maxwell's equations says that if you just take the derivative of the electromagnetic field strength and you anti-symmetrize over all of the indices, then you get 0. And in fact, it's not hard to show that this second set of Maxwell's equations follows directly from the definition of F mu nu as a derivative of a vector potential. Okay. One way of seeing this is to note that this equation can also be written as follows. So you have this 4-index epsilon tensor. So this is the 4-component tensor, which is equal to either 0, 1, or -1, depending on whether mu nu rho sigma is it's equal to 0 if mu nu rho and sigma have any repeated indices, and it's equal to 1 or -1 depending on whether you have mu nu and rho sigma is an even or an odd permutation of 0, 1, 2, 3, 4. Then it's relatively easy to show that this is the same, this is just a different way of writing that equation. And then if you plug in this definition of F mu nu, okay, then it's relatively easy to see immediately that this formula is true. By the way, let me just ask, how many of you have seen differential forms? Okay. So, how many? Okay. So it turns out there's a lovely way of formulating all of this in terms of differential forms. I'm probably not going to do that in this class because even though the formulas are much simpler, sometimes it can make things a little too simple and you can have trouble actually figuring out how to do a computation with it at the end of the day. But you should be aware that all of this has a lovely sort of structure in the language of differential forms. For example, you call A a 1 form and F is a 2 form, and the statement that it's the derivative of the 1 form is just the statement that F is equal to dA. And then this set of equation here is just the statement that dF is equal to 0. So a lot of the equations that we write when we think about this formalism of electromagnetism can be written much more succinctly if you think about the language of differential forms. And a lot of other things are much more clear in this language. I'm probably not going to use this in this course, though. But it is something that you may want to try and look at least a little bit at some point. Okay. Just as scalar field theory is governed by an action, electromagnetism is determined by an action. So, in particular, the equations of motion follow from an action where the Lagrangian is the square of the electromagnetic field strength tensor plus an additional term describing the coupling of the electromagnetic field to the current 4-vector J mu. You guys did this in your problem set, right? So one can vary, it's a little bit tedious if you haven't done it before, but one can vary quite explicitly that Maxwell's equations follow directly by varying this action with respect to a mu and setting the first order variation equal to 0. So the important point, and really the crucial point in our study of electromagnetism, is the observation that the equations of motion of electromagnetism are invariant under what is known as a gauge transformation, where one takes a mu and adds to it a total derivative. So you imagine that lambda is some function of x and t, which is known as the gauge parameter. And you take its derivative and you add it to a, and then miraculously it turns out that Maxwell's equations are unchanged. And in fact, this is very easy to see, because under this transformation, well, f mu nu was the derivative of a, but you had that anti-symmetric combination of mu and nu. So that means that if you take a and add to it d mu of lambda, then f picks up a term which is, well, d mu d nu of lambda minus d nu d mu of lambda. But of course, by the equality of mixed partial derivatives, that's equal to 0, meaning that the electromagnetic field strength is unchanged under a gauge transformation. If you want to think about this gauge transformation a little bit more physically, you can just remember that A0 is the electrostatic potential, which is the potential energy that's felt by some charged particle moving in an electromagnetic field. And the simple case where, say, lambda is a constant times time would just correspond to a shift of phi by the addition of a constant. Okay. And of course, you know that if you take an energy, a potential energy, you shift it by an overall constant, that's unobservable. That's not going to change any of your physics. And so the gauge transformations are really a generalization of this. The thing that's interesting is that the gauge transformations, there's a whole function's worth of gauge transformations. So it's a huge amount of symmetry. And what it means really is that our description of physics in terms of a mu is really redundant. A mu has more degrees of freedom than are necessary in order to describe the dynamics of electromagnetism. The actual fields which have physical content are the f mu nu, So these are the things that are observable. But the A mu give you some redundant over complete specification of the fields. So some redundant description of F mu nu. The advantage of phrasing things in terms of A mu, however, really can't be overstated, okay? Because the equations and the technology that we develop to describe electromagnetism is vastly simpler if we work in terms of the electromagnetic potential instead of in terms of the electromagnetic field strength. Okay. We'll see, not this class because this class is over, but we'll see next class that if we work in terms of the electromagnetic potential A mu, then essentially the quantization of electromagnetism proceeds almost identically to the quantization of a scalar field. Just some few modifications. But this gauge symmetry, this gauge invariance, will then come back to haunt us, and it'll have all sorts of interesting implications for our development of the theory. Okay. So I'll stop here, and I'll see you all on Thursday.